Conical pendulum is one of the property of circular motion. Before that, we should know what is pendulum. Pendulum is a tiny mass assumed to be a point object called a bob connected to a long, flexible, massless, inextensible string and suspended to a rigid support is called pendulum. If the string is made to oscillate in a single vertical plane, this is the vertical plane, and if the bob is get oscillate in a single vertical plane, then we call it as a simple pendulum. Conical pendulum. This is a GIF of conical pendulum and shows that how the conical pendulum performs its circular motion. We can resolve the string of this conical pendulum in such a way that string moves along the surface of right circular cone. So this is a right circular cone. See, this is a right circular cone of vertical axis, and the point object, this is a point object, performs uniform horizontal circular motion. In such case, the system is called conical pendulum. So, conical pendulum is a simple pendulum which is given such a motion that bob describe a horizontal circle and string describe a cone. Consider a vertical section of a conical pendulum having a point mass bob of mass m, and the length of the string is L. Here in this vertical section we have shown all the vectors acting on this bob when it is performing a circular motion. Also, at point position B, the forces acting on a bob are its own weight mg acting in a downward direction and the force T0 due to the tension in the string directed along the string towards the rigid support A. As the motion of a bob performs a circular motion, the resultant force must be horizontal and directed towards the center C of this circular motion performed by the bob, and we can say that all the vertical forces must be get cancelled out, and hence we can resolve the force T0 due to the tension into this two component. One is a horizontal component acting towards the center, that is T0 sine theta, and one is the vertical component, that is T0 cos theta. Here theta is an angle made by the string with this vertical axis at any position. So in this diagram we can say that mg balances the vertical component of the T0, that is T0 cos theta, and the horizontal component T0 sine theta balances the centripetal force, that is nothing but a resultant force which is equal to mv square upon r. From the vector diagram of a conical pendulum, it is found that mg component, which is acting or directed a downward direction, balances the vertical component of tension T0 along the string, that is T0 cos theta, and we can write the equation 1 as T0 cos theta is equal to mg. To get the equation 2, we should see the second horizontal component of a T0 of the string, that is T0 sine theta, which provides a centripetal force and given by T0 sine theta is equal to mv square upon r. In this equation, if we substitute the value of v is equal to r omega, we can write the equation 2 as T0 sine theta is equal to m r omega square. Now we divide the equation 2 by 1. We can write T0 sine theta upon T0 cos theta is equal to m r omega square upon mg. Here we cancel out the T0 factor from left hand side and m factor from right hand side from the denominator and the numerator. We can write the equation as sin theta upon cos theta is equal to r omega square upon g. Rearrange this equation, we can get the omega square is equal to g sin theta upon r cos theta. Considering the same equation, we can write the value of omega is equal to square root of g sin theta upon r cos theta. Here omega is the angular velocity of a ball. From this diagram, we get the value of r, that is radius of a circular motion of a bob, is L sin theta. Substitute the value of this r in equation 3. We can write the value of omega is equal to square root of g sin theta upon L sin theta cos theta. We can cancel out the sin theta term from the numerator and the denominator. We can get the equation 4 as omega is equal to square root of g upon L cos theta. We also know that omega is equal to 2 pi upon t. Label it as a equation 5, where t is a period of oscillation. Comparing these two equations 4 and 5, we can write equation as square root of g upon L cos theta is equal to 2 pi upon t. From this equation, we can get the value of t, that is a period of oscillation, is equal to 2 pi into square root of L cos theta upon g. We also know that frequency of revolution is equal to n, which is given by 1 upon t. Substitute the value of t in this equation. So we can write the equation of n is equal to 1 upon 2 pi into square root of g upon L cos theta. Consider a conical pendulum in a non-inertial frame of reference. From the diagram, at point B, the two forces are acting on a bob. One, its own weight mg directed vertically downward, and second force T0 due to the tension along the string directed along the string towards the support A. The support must be a rigid. As a bob performs a circular motion, the resultant force must be horizontal and directed towards the center of this circular motion. Now for this, all the vertical forces must be cancelled out and we can resolve the force T0 into its two components, one in vertical component, that is T0 cos theta, and one along the horizontal component, that is T0 sin theta. Here theta is an angle made by the string of this conical pendulum with the vertical at any position. Then we can say that when the bob of this conical pendulum is attached to the non-inertial frame of reference, the centrifugal force this which is acting away from the center of this circular motion should balances the resultant of all the real forces, and we call it as a centripetal force, for a bob to be at rest. And we can write down the equation as T0 sin theta is equal to mv square upon r. Again we can write the value of v is equal to r omega in this equation, and we get the equation as T0 sin theta is equal to m r omega square. And also we can get the value of omega is nothing but square root of g upon L cos theta. Here L value of this r is L sin theta. Also we can calculate the period of this conical pendulum as 2 pi square root of L cos theta upon g. N is a frequency of revolution of the bob, and this can be written as 1 upon t, and hence we get the value of frequency of revolution is equal to n is equal to 1 upon 2 pi square root of g upon L cos theta. Period of oscillation of a conical pendulum is given by t is equal to 2 pi square root of L cos theta upon g. So we can conclude that period of conical pendulum depends on length of pendulum, angle of inclination to the vertical, and acceleration due to gravity at given place, and it does not depend on the mass of a bob and angle of inclination if it is very small.